You hit download, and in a second, a massive 4K video file drops right onto your phone. It feels entirely seamless. Because it happens so fast, it's easy to imagine that digital file as something ethereal, just weightless math floating out there in an invisible cloud. But to process that video, your device relies on primary storage, like RAM. Think of RAM as lightning-fast, direct access memory for the processor. It handles whatever you're actively doing right now. But it has a fatal flaw. The moment it loses power, every piece of data inside it is wiped entirely blank. To keep your video safe from a dead battery, that data has to be handed off to secondary storage. This is the vault. It operates independently of the processor's immediate workflow, making sure information is permanently written and preserved even when the lights go out. Saving a file is never software magic. You are quite literally commanding a piece of physical hardware to permanently alter its own internal geography. Take a look inside a classic internal hard disk drive. We are looking right here at a stack of metallic platters, all coated in metal oxide and spinning at thousands of revolutions per minute. This diagram shows what we call formatting. It is the process of building a structural map onto those otherwise blank platters, so the computer knows exactly where to put your data. You can see these dark blue rings circling the center. Those are called tracks. And if you look closely at this extruded piece, you'll see those tracks are sliced into smaller pieces called sectors. Group a few of those sectors together, like this block on the bottom right, and you get a cluster. As these mapped platters spin, a tiny mechanical read-write head hovers just above them. It takes electrical currents and transforms them into microscopic magnetic charges, effectively stamping ones and zeros directly onto those sectors. The engineering tolerances here are staggering. That read-write head is surfing over a platter spinning at highway speeds, floating on a cushion of air exactly 1/1,000,000th of an inch thick. This diagram compares that tiny gap to everyday microscopic debris. Look at the massive scale of a human hair or a single dust particle compared to the clearance under that diskette. If a single particle of smoke or a microscopic smudge from a fingerprint gets wedged into that gap, the mechanical head collides with the surface of the platter. This is called a head crash. It physically shreds the magnetic coating right off the disk. When that happens, you might hear a rhythmic knocking sound coming from the drive. That's the actuator arm frantically trying to read destroyed sectors. Hard drives give us massive, inexpensive storage capacity, but their reliance on high-speed mechanical parts makes them inherently fragile. To bypass the vulnerability of spinning magnets, engineers turn to light. Here we see a DVD and Blu-ray disc, representing the pivot to optical storage. Instead of magnetism, these drives use a high-intensity laser. The heat literally melts microscopic craters into a reflective alloy layer on the disk. These carved-out craters are called pits, and the flat, unburned areas left behind are called lands. To read the data back, the drive swaps that burning laser for a softer, low-intensity beam. By bouncing that softer light off the uneven surface of pits and lands, the sensor reads the reflections as ones and zeros. But to eliminate mechanical movement entirely, we look to solid-state drives. If you look at this top image showing an exposed SSD, you'll see a flat board covered in a grid of memory chips. There are 0 moving parts. Solid-state drives trade the physical vulnerabilities of hard disks for extreme speed and drop resistance. The trade-off is that they typically hold less data and cost significantly more to manufacture. There is no perfect format. Building memory always requires a physical compromise between how fast you need the data, how durable the drive must be, and how much you are willing to pay. Which leaves us with a serious problem. If hard drives eventually break down, solid-state chips are too expensive to scale up endlessly, and optical discs are too small, how does the modern internet safely store petabytes of data? The answer is hardware teamwork. Look at this black enclosure unit. This is a RAID setup, which stands for Redundant Array of Independent Disks. RAID takes a group of inexpensive, fragile hard drives and links them together to form one massive logical drive. By copying your data across multiple disks, if one of them physically dies, the system keeps running and your files survive entirely intact. This redundancy strategy is what allows giant global server farms to keep our data accessible 24/7. They don't use indestructible hardware. They just wire enough vulnerable parts together to outsmart the math of hardware failure. It all scales back down to the device in your hands. Every time you hit save, an incredibly complex chain reaction occurs. The idea of a purely virtual world is a convenient myth. Your data always comes down to an aggressively physical symphony of spinning magnets, melting alloys, and firing silicon.